Good afternoon, everybody. This is the last session, and this is pretty short presentation here. One of the things that recently we have been working with community, and also we have been looking into HPC and machine learning from the networking standpoint. So in this talk, what I'm going to cover is give you an overview of those benchmarks. Where are some of the gaps? And then, since this is part of the server project, within that there is whole HPC sub-project, how we can, as a community, contribute to this one. And then I have a proposal, would like to get an input from the community on that. By the way, quick intro about, I am a distinguished engineer at Broadcom. I also lead hardware management project at OCP. This is joint work with Dr. Panda from Ohio State University, who has been working in this area for quite a number of years. Unfortunately, he couldn't be here, so I'll be giving the whole presentation. So what I'll do is introduce this benchmarking, go over two categories of benchmark, micro benchmarks, and some of the application benchmarks, and quickly point out the gaps how we see it, and then we'll get into what can OCP as a community can do to help with this. So machine learning, AI, HPC, this is where all the this need for more and more processing power, higher network bandwidth, more and more distributed parallel computing. It's always been the case, and it never stops. If you have something right now, there are already demands for the next generation, which are twice X, 4X higher than that. And this is mainly driven by a lot of these applications. They do have huge amount of data, and they use all different types of parallelism, like whether it's a model parallelism, data parallelism, and this massive amount of data is distributed across multiple nodes. So there's already local computation going on, and then there's a lot of data exchange that goes on to get to whether it's one reduction operation or exchanging the entire data set that everybody worked on their part of it. And this is where you start getting into what are the communication, why we want to benchmark, because a lot of these operations are about where all nodes are participating, and on each node you will have multiple processes. General model, you use one process per CPU core. So there are so many cooperating processes. They're trying to perform an operation like all reduce, a simple operation across the data set. They have done all the processing on their data set, and now they want to exchange all the data across all the nodes, so everybody gets the full view of the entire data set. So that's where all this, what we call the collective kind of operations come into picture. There's also a point-to-point kind of or near neighbor kind of communication that also happens, where you are using send-receive kind of semantics, RDMA reads writes to exchange that kind of data. And then all these collectives we see beneath it are using, whether you are using collective libraries or MPI libraries, underneath you have all the RDMA style messaging going on. To add to all that, what you have physical topology, traditionally in OCP we talked about this networking infrastructure. We generally talk about the physical infrastructure. But at the application level, they're using a different logical topologies, whether you're communicating in a tree-like structure, or you have binary, you have cube-like, or you have other topologies, and generally they are not fixed. Depending on the number of processes, number of nodes, you might be selecting a different topology, which is optimized for a given communication operation. So these are the things which are really interesting from the overall performance standpoint, but you really want to understand this from a benchmark standpoint. And that's where what we have been looking into, this different class of benchmarks that are out there and what is missing in there. So here on this chart, you see there are two classes. First one, generally everybody kind of talks about specific performance metric. This is where the micro benchmarks come into picture, whether you're measuring unloaded latency from a point to point, or you're measuring total time taken by a collective operation. And typically what happens with this kind of benchmarks, it starts with one of the operation, involves the libraries and below the software layer and low-level APIs. And then, of course, the provider architecture, which includes software and hardware components, as well as your network infrastructure. So that class of micro benchmark is targeted towards a specific operation, whether it's a point-to-point or a collective operation. So that's one class. You have, on the other side, you have application-level benchmarks, and I'll get into some of those examples. But these benchmarks, they tend to run a specific application, or they tend to mimic some domain-specific application computation and communication. And end of the day, what you get is the total completion time for that application. And that's what you use. And then you also look into how does that scale as you increase the number of nodes, number of processes per node. Completion time is one thing. There are also simulation times. So depending on what matrix you're using, you want to see the scaling across as you're distributing. So generally, that's how people use those application benchmark. Again, that also involves a specific application and then the libraries and all the layers below it. So these are widely used benchmarks in both HPC and machine learning, whether you start with the micro benchmarks and then you have a specific set of application benchmarks. Let's look a little bit more into this micro benchmarks. I did mention the latency and bandwidth. So you have very simple RDMA perf test kind of application. What you're doing is you're setting up between two endpoints connection, and then you're transferring some data using specific operation, whether it's a send, RDMA, write, or read. And you just measure the unloaded latency. Unloaded means nothing else is going on the network. You're just measuring that point to point. Same thing with the bandwidth. Then you start getting into some MPI level benchmark, like Ohio State University has what they call is Ohio OSU micro benchmark, OMB. Intel has something equivalent of that, IMB. What these benchmarks do, they have a set of collective operation, and then you can basically measure the performance of individual collective operation. And recently what has happened is with the GPU becoming more and more used in this kind of environment, where you have GPU-specific libraries which provide this type of collective operations optimized for a specific architecture, and also across the network then. So there are also benchmarks which allow you to just measure specific operation for a given GPU-specific library. So what is missing here? So what you're getting with this micro benchmark is you get to understand that if you have nothing else going on, and if you have just the communication happening without anything else on the network, this is the raw performance you can see. Does that really reflect the application level communication pattern? Not really. And also there's no computation communication overlap. So what's the impact of that is also something you can. So these micro benchmarks are good for your initial evaluation of raw communication performance, but it's not sufficient. This one shows an example of Broadcom 100 gig adapter. This is what it looks like. When you run those micro benchmarks, you get, and based on that, you can say very low latency for messages, and I'm getting wire speed throughput going beyond certain message size. Now, if you are an application developer, it doesn't give you much about how will your application behave with this kind of communication below it. So that's one side. The other side is, and this applies to both HPC and machine learning applications, where there are different domains, whether computational fluid dynamics, simulation models for molecular dynamics. They're all scientific kind of computation. And what they do is, end of the day, they take a problem domain, decompose that into subdomains, and those are generally assigned to a specific node or specific process. And then there is some near neighbor kind of communication happens depending on how the data is exchanged. And also there are collectives involved where everybody's participating into getting to the final solution. So these are good if you are interested in a specific application and just measuring the performance of that for a given infrastructure that you have, given communication infrastructure. Can we do better? Sure. I think what will be helpful is to mimic the communication patterns that are going inside this application and maybe come up with a set of those where it allows you to measure the communication aspects without running actually large data set, and because they all take a long time, and also still be representative of what that application might do. So this is showing examples from HPC. Machine learning, similar story there. I have listed some of those here, but these are some of the standard benchmarks people use. They look at the performance. This is whether it's their training model or their application. There are open source implementation, Param benchmark, which is PyTorch based. So this does give you, okay, if you have this type of your machine learning application, this is the specific model you are using, how will it fare for a given topology? But it doesn't really go in detail into communication. Also, it doesn't really talk about what happens if I have congestion in the network. So these two spectrum, they kind of leave us with, there are still some gaps. As I mentioned, that it will be beneficial to have tests which can have this kind of communication patterns that you can model across multiple applications and maybe come up with a subset which says, okay, this set of applications require this kind of communication. This is how they scale. As you change the application or message size, the topology selection changes. So having the ability via benchmark to test that kind of communication pattern selection of topology, that's a gap that we do see today. And then the second gap here, what we see is it's always computation and communication always together. But can we just focus on the communication part so that you can understand if you have this compute part, how will the communication fare? What kind of performance you can expect from the underlying network? And you can evaluate different topologies and see, okay, if I use this, I may see better performance. If this is communication intensive operation, maybe I should select this kind of topology. And then you combine all this and add to that the actual congestion, because generally HPC machine learning, they have dedicated systems, machines, they're running dedicated application, but we are seeing now you may be running multiple applications together. There may be storage traffic that's going over network. There may be virtualized environment where you might be running multiple applications, other applications using the network. What this creates, even within the same application, when you do some operation, it may create network congestion. So when that happens, how do you fare? So today, we do not have benchmarks which allow you to measure the congestion control aspects for this type of application. So that's the proposal here, that we have these two ends of benchmarks for HPC, and then we have this HPC sub-project within OCP server project. We can create a class of benchmarks which will get us closer to those applications, allow us to model the communication pattern, measure with the congestion, what is the impact of congestion on different aspects of the application performance or communication performance. So with that, and I kind of talked about this, but there are two classes, micro benchmarks, application benchmark. There are gaps, as I highlighted, and there is a need to create this new class of benchmarks. OCP servers are widely used in these applications. We do have this sub-project. So proposal here is to promote this new class of benchmarks. Not only that, what I would say as a community, it will be good to study this HPC machine learning workloads, come up with a good benchmarking methodology which will help overall, those who are using OCP servers to do this, to run this kind of applications. And then out of that, this sub-project within server, we can come up with also some extension to this benchmark, which can be common across. We can work with other organization and to close these gaps. So with that, I want to take a pause, but would like to get, this is something new for server project, especially for HPC sub-project within that. And I would like to gauge what's the interest in working on this kind of work stream within OCP. Any questions? I think.
All right, thank you very much.
Okay. Thanks.